Welcome to Allied Vision Answers. Infrared cameras with in-gas sensors often feature sensor cooling. Why is that, and is it necessary? To answer these questions, I'm calling in Josh Hagen, Product Manager of Infrared Imaging at Allied Vision.
Yes, thank you, Francis. There are two aspects that need to be considered to answer your questions. At first, the temperature of an in-gas sensor has an impact on its spectral sensitivity, which means how well it captures infrared light at specific wavelengths. The quantum efficiency curve of a sensor shows its sensitivity over the electromagnetic spectrum. An in-gas sensor typically has this kind of shape, and it is typically sensitive between 900 and 1700 nanometers. Depending on the temperature, the response of the sensor varies in both its efficiency, that's the vertical axis, and the wavelengths, that's the horizontal axis. The deviations may not be so important in their absolute value, but if you are using an in-gas camera to perform measurements over time, temperature variations of the sensors can significantly change its sensitivity at a given wavelength, especially at the edges of the efficiency curve, as you can see in this example. So the issue here is not so much whether the sensor is too cold or too hot, but rather whether its temperature is constant or changes over time. In that case, it may falsify the data captured by the camera. In applications that require constant, repeatable results, it is important to use cooling technology to keep the sensor at a constant temperature. In fact, you may even want to use both cooling and heating to maintain a stabilized temperature. The next reason why sensor temperature is important is dark current. Because of their technical composition, in-gas sensors tend to produce a higher dark current than pure silicon-based image sensors used for visible and NIR imaging.
What exactly is dark current?
So the basic function of an image sensor is to convert an electromagnetic radiation, in this case the light, into an electric signal. If the sensor is exposed to no light at all, in theory it should not provide an output signal. However, in reality a background signal always remains. This background signal that is always there, even in the dark, is called dark current, and in in-gas sensors it's quite high. Because of this dark current, the image captured by a sensor exposed to complete darkness is not perfectly black, but includes lighter pixels, which is what we call noise in the image, as you can see here. In this example, I have selected a 200 millisecond exposure time. Why have I done that? Because typically in dark setting, you will want to have a long exposure time to capture an image. But unfortunately, the longer your exposure time, the noisier your image will be.
Why is that?
That is because the level of dark current depends a lot on the exposure time to capture the image. A short exposure time will generate little dark current and hence little noise, while a long exposure time will generate a higher dark current and more noise. The relation between exposure time and dark current is linear, as you can see on this curve. So dark current noise may not be such a big issue for images that are taken at short exposure time, but the longer the exposure time, the bigger an issue it becomes. An even more important factor that impacts dark current noise is the sensor temperature. The higher the temperature, the more dark current-based noise you will have in your image. In fact, dark current typically doubles for every 6 to 8 degrees Celsius sensor temperature increase. So that means that dark current increases exponentially with growing sensor temperature.
And that's why you need cooling, right?
Yes, but the good news is, if you can reduce the sensor temperature, you will reduce dark current noise considerably. Here you can see the noisy dark image delivered by an in-gas sensor at 40 degrees C when exposed to darkness at 200 milliseconds exposure time. And on the right-hand side, you can see the same image captured by the same sensor at the same exposure time cooled down to 0 degrees C. As you can see, the noise is now strongly reduced. Of course, the dark current noise is not only present when the sensor is not exposed to light. It is always there as background noise. So here is an example of an image captured by the same sensor at the same exposure time at plus 40 degrees C and 0 degrees C. As you can see, the sensor cooling significantly improves the image quality by reducing noise.
Okay, now I understand why cooling is so important. But if in-gas sensors need to be cooled, or at least maintained at a constant temperature, why are there in-gas sensors or in-gas cameras without sensor cooling? Does that mean that sensor cooling is not always necessary?
Let me show you an image captured out of our lab's window with our Goldeye SWIR camera. This image was made without cooling at a sensor temperature of 45 degrees C. And now the same image, captured with the same camera, cooled down to 20 degrees C. You can see some slight differences in contrast in the sky, and if you compare the histograms of both images, you will also spot small differences. But overall, the difference is not obvious and the quality of the uncooled image is pretty good. This is probably because the outdoor scene was bright enough to allow for a short exposure time, so that dark current noise is limited.
So when would I need cooling and when would I not?
This depends on the type of application you have, and one of the main criteria is the exposure time that you need. This table shows some examples of applications. If you are performing a simple daytime surveillance task, your scene will typically be properly illuminated, which means you can go with a short exposure time. Deviations over time are not that important, so you may not need cooling. If you are performing hyperspectral or multispectral imaging, your illumination may be sufficient for short exposure times, but you also require a precise and constant spectral sensitivity, so you need at least temperature stabilization, hence a sensor cooling system. Let me show you an example of an application where cooling is absolutely necessary: photovoltaic cell inspection. You can detect cracks and defects in the solar cell substrate by applying a voltage to it. As a result, it will emit infrared light per electroluminescence that will make the defects visible to an infrared camera. However, the intensity of this luminescence light is very weak, so you need very long exposure times to capture a usable image, up to 10 seconds. As a result, the image is very noisy, so it's difficult to detect defects. In this case, it's much better to cool down the in-gas sensor to -20 degrees C to achieve a low noise image that will allow the system to detect cracks and sort out defect cells.
So cooling is essential for low light applications, but may not be necessary if I have a short exposure time. But if I need sensor cooling, which one should I choose? I'm sure there are different types of cooling, right?
Exactly. So far we have learned why and when sensor cooling is necessary. But let me now introduce you to the different cooling techniques that are available and present you their pros and cons. Fortunately, in-gas sensors do not require costly Stirling coolers used for mercury cadmium telluride or MCT SWIR sensors. Typically, in-gas sensor cooling is achieved by attaching a thermoelectric cooling module, in short TEC, to the back of the sensor. You may also have heard of them as Peltier cooling modules, which refers to the physical effect that these modules apply. These TEC modules generate cold on one side, and if you thermally connect the sensor at the cold side, you can easily cool down the sensor. There are multiple stages of thermoelectric cooling possible: TEC 1, TEC 2, TEC 3, and so forth. And obviously, there's also the option to not cool at all. The more stages are used, the larger the drop in temperature that can be achieved. Typical values are -30 Kelvin for TEC 1, which equals a temperature difference of -30 degrees C, -60 Kelvin for TEC 2, and -80 Kelvin for TEC 3. So by using TECs, you can cool down your in-gas sensor to extremely low temperatures. However, this is not an easy thing to do, and there are technical challenges.
How come?
Basically, there are two main technical challenges when using thermoelectric sensor cooling in a camera. The first challenge is condensation. If you cool down your sensor to a very low temperature compared to the ambient temperature, the humidity of the air will condensate as water drops on the sensor, just like on a cold beer glass in the summer. Nobody wants that, as it could damage the sensor and cause image artifacts. The second challenge is heat. It may sound paradox, but TEC modules produce heat when they cool the sensor. Actually, it is quite logical, as they consume energy to produce cold, just like the refrigerator in your kitchen. It is cool inside, but the compressor in the back heats up. This is an issue because it heats up the camera and therewith also the components used inside, like the sensor. So at the end, it's a kind of devil's circle. The more you cool the sensor, the more you heat it up and the more you need cooling. There are different ways to address these issues depending on the power of the TEC module. As we saw earlier, TEC 1 is the lowest stage of cooling. With such basic cooling, condensation is in general not a big issue and heating can be addressed with passive heat dissipation. The principle of heat dissipation is to cleverly design the camera so that the TEC module is physically connected to the external housing of the camera with heat-conductible metal parts. That way, the heat is transferred to the outer shell of the camera and dissipates in the ambient air via the large surface of the camera body. The design of the housing may maximize the air contact surface with the integrated cooling fins. If this is not enough, you can mount heat sinks on the camera body to increase the air contact surface even more. Applying TEC 2 cooling is more challenging because it can reduce the sensor temperature by up to 60 Kelvin. That's twice as much as TEC 1. As a result, condensation can easily happen on the sensor glass. Additionally, the TEC 2 module also heats up stronger, and passive heat dissipation is not enough to get rid of the heat inside the camera. To prevent overheating, the camera needs to be fitted with a fan that will ventilate the electronic components. And to prevent condensation, the sensor must be enclosed in a sealed chamber filled with vacuum or an inert gas such as nitrogen. This ensures that no air gets in contact with the sensor and hence no moisture condensates on the sensor. The fan and the vacuum chamber help to resolve the condensation and heating issues. But such components need more space. So typically, a TEC 2 camera is larger and heavier than a TEC 1 camera to accommodate these additional components. TEC 3 cooling modules are even more powerful than TEC 2, which means they also need a sensor chamber and even more advanced heat dissipation measures. This could be a larger fan or even a water cooling system, which makes them even bulkier and more complex to build.
Okay, so there are pros and cons to sensor cooling as well as different cooling technologies?
Exactly. Let me summarize. On the pro side, we saw that cooling helps reduce dark current noise. Cooling also helps to stabilize the sensor temperature and hence the sensitivity of the camera. With a stable image quality, you can apply image correction algorithms more efficiently. For example, to eliminate the defect pixels or to get a uniform image. Cooling allows you to implement long exposure times in low light applications. It also improves the image quality by achieving higher SNR and dynamic range values. So all in one, the sensor cooling improves the image quality, and this is particularly true for demanding applications requiring long exposure times. On the con side, we also saw that a TEC module consumes energy, which increases the power consumption of the camera. Sensor cooling typically results in a larger and heavier camera design. For TEC 2 and above, you need active cooling of the camera, which makes the camera more complex, less durable, and less rugged for industrial applications. If the camera is equipped with a fan, this fan can generate vibrations that disturb image capture. Here it is important to choose a camera that enables to switch off the fan during image acquisition. Depending on the operating conditions, condensation may become an issue that can be resolved by integrating the sensor into a nitrogen or vacuum chamber. But it adds up on size and weight and requires a very advanced manufacturing process. So all in one, sensor cooling means a more complex camera that will be bigger, less durable, and more expensive. Therefore, as a conclusion, I can say that sensor cooling is essential to achieve a good and a reproducible image quality in SWIR imaging applications, especially under poor lighting conditions. But you should always question if your application really requires it, because if not, you can save size, weight, power, and cost by using an uncooled camera.
Thank you, Jens.
You're welcome.